Now remember, we are testing a hypothesis. We just went through a whole thing and we determined the time that it would take for a seismic wave to leave an earthquake and travel through the Earth to each one of those stations if the Earth were solid rock. So to test this, we need to compare these calculations to what the actual arrival times are. Scientists do this all the time. We make predictions and then we test it in real life. So now we're going to look at the actual recorded times by the seismic stations in our records section. So you probably have this done. We did this the other day, but if you don't, this is a pretty simple since the records section has time along the y-axis. So take a ruler and you're going to line it up with the beginning of the P wave of each station. Now the P wave is where we have that first big anomaly, that first big jump. Now, a lot of your pieces of your record section have some activity, like a bunch of little squiggles. You want the first big jump in your record section. And the easiest thing to do is line up a ruler along the beginning of the P wave and just read it across. So if we look at station number 1, if we line up our line and we go over, we can see that that wave arrived at the station 1 minute after the earthquake occurred. So do that for each one, and you're going to record this as the actual travel time. So now we're going to go back to our Colab and edit our data table with this information. If we scroll down from the graph that we just made, there's a new code block. Now, if you have closed Colab, you will need to run all of the blocks from the top. So you can go up to the menu. There's a menu called Runtime. Click on that and choose the Run All option, and it will run all of the blocks in the code from the top. Now, all these will reload, and you'll get some errors in the blocks that you haven't changed yet, but we're gonna fix that. So start here with the actual arrival times. So this is very, very similar to what we just did. We're going to add in those actual arrival times that we just read off of the record section. We're going to add this in as an array since it is data, and we have recorded that. So remember to get rid of the apostrophes and put commas in between each data point. You should have 17 of them. And with no errors, you should have a nice new data table that finally has all of the data that we need to do our analysis. So we're going to take that fancy new data set and we're going to make a graph. Now we're going to get a little nifty on this because we want to compare two sets of data. And the best way to do that is put both data sets on the same graph. So in this code block, go through and fill in the necessary information and create your new graph. So anywhere that it says something like, which column of actual data do we need? You want to put the name of the actual data. Remember, it has to match exactly, or it's not going to work. So pause here, create your data, or create your graph from your data table. So now that we have two graphs, let's compare them. The red dots represent the predicted arrival time of a seismic wave to go to a station if the Earth were solid rock. That's the red. And that was that nice, smooth little curve. The blue dots represent the actual arrival times of the seismic waves of the 2010 Haiti earthquake. Now first, the waves arrive at the station pretty much at the same time that we would predict. So if you look at the blue and the red, those are pretty close. The red is the prediction, the blue is the actual time. So we can say for this part right here, yeah, that's definitely true. Our predictions were correct. So for small geocentric angles, the arrival time of a seismic wave to a station is just what we would predict if the Earth were made up of solid rock. Now if we look up here at the top too, same kind of thing happens there. So the last little part, those waves arrive a little bit later than predicted at about 120 degrees. And then earlier, so this is the section that we're really interested in this green circle, because our predictions really are not matching what is actually happening there. So something is interrupting the energy between about 100 degrees and about 125 degrees. So those stations that have a geocentric angle between 100 and 125, is that a question? Like now, so are we saying that the Earth is not solid rock? That's an interesting question. So what does this look like on our model? Let's kind of sketch something out here. The first station here has a geocentric angle of about 25 degrees. And from the epicenter to the first station, the predicted arrival time was the same as the actual arrival time. So that must mean that everything that the seismic wave traveled through between the earthquake and the station at 25 degrees was solid rock. So we can draw a line here, and we can say that anything between the earthquake and the station was solid rock. We're going to shade that in with red. Now the second station here has a geocentric angle of about 60 degrees. This is still within the range of angles at which the predicted arrival time is the same as the actual time. So we can shade this area in too. So all of this red we assume is going to be, we can say is solid rock because the predicted times are the same as the arrival times. Now, according to our data, any station that had a geocentric angle that was less than about 100 degrees from the earthquake showed an actual arrival time that was the same as the predicted. So anything up to this point right here on that green line is about 100 degrees. So any station with a geocentric angle of about 100 degrees or less will show the seismic wave arriving just as we would predict if it were traveling through solid rock. So what we can say is all of the waves that are leaving the earthquake and going to anything less than 100 degrees, that must mean that everything above that direct line from the station to the earthquake would be solid rock. Now keep in mind that we have only been looking at one half of the Earth, but we know that the energy from the earthquake is going to spread out in all directions. So we can also draw the same conclusion for the other half of the Earth. Remember that we are using the geocentric angle to measure the location of the stations. So we are plotting the stations on a two-dimensional map, while in reality, they are not all in a nice little straight line along the surface of the Earth. From this, we can conclude that not only does the 100-degree angle hold for the stations up from the earthquake, but also down and to the left and to the right. So this means when we can draw that line to 100 degrees down from the station as well. This is starting to kind of map out where we have evidence of where the solid rock is inside the Earth. Now what if we had an earthquake on the other side of the Earth? We can assume that this 100-degree angle will hold true no matter where the earthquake occurs. So our data will show the same thing, just from the other side. So this is going to let us start to kind of map out where along these lines we have solid rock inside of our Earth. Now you have a paper. There's a very small model of your Earth. And on this paper, I would like for you to make 10 marks around the Earth to represent the epicenter of an earthquake at that location. So we want to narrow down our area that is not solid rock. Once you do that, you're going to use a protractor to measure an angle of about 100 degrees in both directions, just like we did on our big model. And we're going to do that for 10 different locations. And so once you get that done, you're going to have kind of a map of where there is solid rock and where there is not. And the more data points you have, the better data we're going to have. So now that you have that, what do you think this inner circle represents? Compare what you have to what your textbook says about the interior of the Earth.
Yes, we have textbooks. If you look over on the shelf over by the door, there are some blue textbooks. Those are earth science textbooks. Page 308 to 316. It says 8 pages, but there's a lot of pictures. I think you can handle that. And I want you to look at those statements in that particular section of your textbook, and I want you to see whether or not your data supports what is written there. Now remember, we were testing a claim. The claim is that the Earth is solid rock. When we started out, we created a model of the Earth that lets us predict the arrival times of seismic waves from the epicenter of an earthquake to different seismic stations. We used the graph created from that model to create the actual arrival times of the waves of the given stations. We found that some of the stations did not have seismic waves arrive at the predicted time. So that means that we must conclude that there was something other than solid rock between the earthquake and that particular station. So you're going to write a claim evidence reasoning statement, whether or not your data supports the claim. Now this one gets a little bit tricky. So the first sentence, we're going to restate the claim. What is it? What is the goal of our project? And who did you work with? And what did we call it? So the first statement is an introduction. The second statement, you're going to answer the claim in at least one complete sentence. So this is whether the data supports that the Earth is solid rock. Now keep in mind, our data showed 2 different parts of this claim. So you want to qualify your claim, yes or no, with that piece of evidence. Because that evidence is going to support your claim. You're going to cite your data from your Earth models to support your claim. You also probably want to cite some data from your small Earth model, where you drew multiple lines, multiple 100-degree lines. You can also cite data from your textbook. So you need data from at least 3 different places to support your claim. And then you're going to explain the reasoning. Why does that data support your claim? What is it that data shows is true that makes you know whether or not the Earth is solid rock or not? And then your last sentence is going to be a summary sentence. Prove your point one last time, but just kind of summarize it, and do not add any new information. So your summary should not have new bits of information. So you should have at least a very minimum of 5 sentences, probably a few more.